Okay, the next section we're going to take a look at here, or at least the next part of this section, 6.1, is what if we have a function of y instead of the usual and familiar function of x? Well, this just means instead of a function of x needing to pass the vertical line test, things shift. So a function of y would be something that needs to pass the horizontal line test. So when it comes to determining the area between two curves, when those curves are more naturally or most naturally presented as a function of y, we need to not worry about which graph is above the other. Rather, we need to determine which graph is to the right of the other. So instead of top minus bottom for the area between two curves, it's going to be right minus left. So it really boils down to determining which curve is the right hand boundary and which curve represents the left hand boundary of our region. Okay, so everything else in a previous video we talked about, we spent some time talking about and developing the idea of what it means to be, what it means for a region, I should say, to be vertically simple. We now have an analogous definition for horizontally simple. So for horizontally simple, a region would be one in, a region would be where doesn't swap which graph is to the right of the other. So for instance, if we look at this graph, if we consider the other function to be this x equals 0, the y-axis itself, then the full region here, this shaded piece, and this shaded piece all together, then this region is not horizontally simple. Because for this top region, the right boundary curve is y squared minus 9, and the left boundary curve is x equals 0. But for this next boundary piece, you can see that they have intersected and they have swapped. So now the right-hand boundary is x equals 0, and the left-hand boundary is this horizontal parabola. So it's that same idea as what we had with vertically simple, but now we're shifting it to horizontally simple. Okay, so let's take a look at an example here. Example 3. Determine the area of the region between these graphs, e to the y and y squared minus 2 for y between -1 and 1. So what I would do here is I would essentially remind ourselves that we can just think of this as x equals e to the y and x equals y squared minus 2. You're all familiar with the idea back in Calc 1 or even pre-calc before that. If you've got a function f of x, you can always say f of x is equal to y. Well, similarly, if we have something that's a function of y, we can always just say that's equal to the x values. So that's how we can write these two down. And now you might not really know what x equals e to the y looks like. But you could manipulate this equation by taking the natural log of each side. And then the right-hand side, we have our composition. We're composing inverse functions. Natural log and e are inverses, so this would just simplify to y. So the graph of x equals e to the y is exactly the same as the graph of y equals natural log of x, and you all should know what that looks like. So feel free to manipulate these equations if it helps you graph things. So the natural log of y looks something like this. So I'm going to write x equals e to the y, though. You're welcome to put y equals natural log of x, but you may find yourself needing to use this equation, so that's why I'm just labeling it this. It doesn't actually matter because they, as we have just determined, they are equivalent. And remember, for natural log, there's a vertical asymptote here at x equals 0, so this just plunges down to -infinity. Okay, what about this one? Well, you all have a lot of familiarity with parabolas. So we know that what I would say is think about what do you know about y equals x squared minus 2? Well, y equals x squared minus 2 would be a parabola like this. It opens upward because the coefficient is 1, which is a positive number. So it opens upward. And the intercepts here would be plus or minus the square root of 2. Okay. So we can use that same idea here and think about it here. So this parabola opens in the direction of positive y because the coefficient of the largest degree term is positive. So this will eventually be a very large positive number. So since this is equal to y, that means this will go in the positive y direction. So similarly, we can use that same argument here. The coefficient is 1, which is a positive number. So this would open up in the direction of positive x. So this would be a parabola that looks like that. The not x-intercepts, but y-intercepts would be plus or minus square root of 2. So we do have something that looks like this. I'm going to go ahead and just continue this down. This might be drawn a little bit not to scale. Well, certainly not to scale, but let's add a little bit more. Okay. So in this case, our parabola, I'm just going to add just a little bit more. Our parabola here might do something like this. Okay. Try my best to make this as symmetric as possible, but you know, it's not always easy. Yeah, that's about as good as it's going to get. There we go. Okay, so this was x equals e to the y, and this curve here was x equals y squared minus 2. Okay, so this value here is positive root 2. This value here is negative root 2. Keep in mind that the square root of 2 is approximately 1.414. So we are only interested in integrating for y between negative 1 and 1. So there's going to be, let's see, some value here. Draw these in blue. So let's say there's y equals negative 1, and here, y equals positive 1. So our region looks something like this. I'll shade this in red. That is a strange one. Okay, so we need to identify the left and the right boundary of this region. So here, the left boundary is this curve, which is the parabola. So this is x equals y squared minus 2. And the right boundary piece would be x equals, well, it's this e to the y. Okay? So our area between these two curves would be the integral of right minus left dy, and then we'd integrate from negative 1 to 1. All right. So, oops, let's go ahead and just simplify this a little bit. This is e to the y minus y squared plus 2 because of that double negative. And then we can integrate now. So the integral of this, I'm going to move up here. So this is, let's see, we've got antiderivative of e to the y is e to the y. Then we've got minus 1/3 y cubed plus 2y between negative 1 and 1. So e to the 1, which is e, minus 1/3 plus 2 minus what we get when we plug in negative 1. So e to the negative 1 minus 1/3, but when we cube a negative, we get a negative, so this becomes double negative, so plus 1/3. And then we have plus 2 times negative 1, so minus 2. This should all simplify into e minus 1 over e plus 10/3.